So let's get into separable equations. We mentioned this yesterday. And separable equations are like the nicest form of differential equations, because it's really just like back to the basics of Calc 2. If you have to take a higher differential equations course, differential equations, I tell people, is it's like Calc 2 on crack. It's like the beginning of Calc 2 when we're just learning all these techniques, these U-subs, these trig subs, integration by parts. Differential equations is just more tricks, except solving these more complicated differential statements, differential equations, and learning how to integrate and come up with a solution for them. So the easiest ones we can do with just kind of the basic Calc 2 stuff that we've done are separable equations. And I mentioned that they're equations of the form first order differential equation. So it's just going to be something like dy dx. And it's nice enough where we can factor the functions. In some sense, I can factor out all the x's and all the y's, and it just looks like a function of x times a function of y, or divided. Of course, depending on how you write the function, you can write the function as 1 divided by something to get a multiplication. H of y. So something to that effect. Of course, and we could even flip those. Could be h of y over f of x. Really, the idea is I can just factor it either as a multiplication, as a product, or as a division with only x's and only y's, and I can separate them, really. So the best way to just look at these is just to see some examples. So let's actually start off with one that we've looked at. We've seen dy dx is equal to negative x over y. And remember that the vector field for this guy we saw was circles. Here, actually, let me do these in blue. Those are my axes tick marks, but right. So when y is 0, this expression is going to blow up to infinity. So whenever y is 0, my slope is infinity. So we're drawing these vertical slopes. Whenever x itself is 0, now I'm on the y-axis, the slope itself is 0. So if the slope is 0, we're drawing horizontal slopes. And then we mentioned a few other things you can look at, like if x is equal to y, so x equals y is our 45 diagonal line. So on that line, 1, 1, 2, 2, 3, 3, we're always going to get negative 1 as our slope. And that even includes the negative numbers. And then likewise along the line, x equals negative y, or y equals negative x. So that's what, 1, negative 1, 2, negative 2. We will get a positive 1 slope. So we get a vector field, or a slope field, that looks kind of like this. And we plotted some other ones just to get the slopes, and just to get the idea that, yeah, this should look like a circle. Here, we do a few more. So something to that effect. So let's actually show that now. So how do we actually solve this differential equation? We can kind of see that if I were to draw my slope fields, we should get these circles as solution curves. So we have an intuition of what it should be. We want to be able to actually solve it, of course. And the way we solve that, since the x's and y's are separated, you essentially multiply or divide and get all the y's on one side and all the x's and dx's on the other side. Just like we've been saying with our integrals. whether it's a u sub or a trig sub with thetas, you want the differential to match the variable. So let's just match those up. If I multiply the y over, we've got y dy equals negative x dx. And then to solve that, we just integrate both sides. And what do we get? So that's 1/2 y squared equals negative 1/2 x squared plus a constant. So in all these separable equations, it's just common practice to put the plus a constant with the x variable. Since ideally we want to solve for y as a function of x, if we can, we usually just like to keep the constant over with the x's. Theoretically, we should have a plus c here and a plus indifferent c here, but then I can always take one of the constants and subtract it over and combine all the constants on one side of the equation. So we don't really need to have that extra constant with the y integral, since we can always just combine them. So now solving for x and y, if we wanted to actually sort of keep this a little more formal without solving for y, we can write it as, well, 1/2 y squared plus 1/2 x squared equals a constant. And if I multiply everything by 2, what do we get? Y squared plus x squared equals 2 times a constant, still just a constant. So this is, again, another slight abuse of notation. If I multiply everything by 2, constant, still a constant. Since it was a dummy constant, we don't really need to write 2 times a constant. If it's a specific constant sometimes that we're solving for, sometimes you do want to keep the 2's in the manipulations, but because it's just a dummy constant that could be anything, it's fine to keep it as it is. And what's our equation? X squared plus y squared equals a constant. That is equations of circles. With square root of c as the radius. And so this, of course, depending on what initial information we were given, we could solve for the constant and we would know exactly which circle we were specifying in that case. Let's see some other ones. So these can get kind of tricky, at least solving for y. I mean, I guess not tricky in terms of solving, but we can throw all the functions at you. So you kind of just have to remember all your derivative integral tricks. Let's see. So we've got an example. 6x squared over 2y plus cosine y. So again, we've got all of our y's in the denominator. We're going to multiply those over to get 2y plus cosine of y dy is equal to 6x squared dx. We integrate. And this one, I guess, isn't too bad, since you just have to remember the integral of cosine. There's no trig subs or anything we need to do for that. We'll have y cubed times a constant of 2/3 plus sine y is equal to 2x cubed. And we have our plus a constant over here. And in this case, it looks like we're done. A lot of times we want to try to solve for y. In the last case, of course, if we wanted to solve for y, you do just have to remember that when I take a square root ourselves, when we apply a square root ourselves, you remember the plus or minus. So there's really two families of functions, at least y as a function of x, that will solve this equation. Our upper half of the circles and the lower half of the circles gives us the two separate functions. And for this equation, sometimes we simply just can't solve for y. So this is the type of situation where it's basically an implicit function. So if you remember from Calc 1, doing implicit differentiation and implicit functions, we just leave it as an implicit function. And if we were given initial conditions, a point of y, to solve for a point of x, I could solve for that constant. So maybe we make one up here. Let's see. So let's say we have the initial information that sometimes we give it as a point. So it could say, let's say when x is 1, y is 0. That'll be something to plug in. Otherwise, sometimes they could write it like y of 1 equals 0. And then we would just plug that in. So we've got our x and y. So y is 0, nicely enough. We will just have 0 on the left. On the right, we've got 2 times 1 plus our constant. So our c is going to be negative 2 in that case. And so our implicit solution will be to the curve that satisfies this equation. So nothing big there, just solving for a constant. Let's see. So some other ones we've done, or at least seen. Let's do this one. So this one came up on our vector field matching equation. dy dx is 1/4 y times 4 minus y. So on our vector field matching, how did we pick this out? You want to pick easy values for y and x. So like we were just doing in the last one, look for where this is 0 or where it's infinity. So in this case, it's just a polynomial. And you can see that when y is 0, it'll kill the whole thing. So whenever y is 0, my slope is 0. So y is 0 is the x-axis. So we should see horizontal lines, slope of 0 on the x-axis. And likewise, when y is 4, the whole thing will be 0. So we can go up to 4. Just put dots for the tick marks, 2, 3, 4. And so we should have seen horizontal lines at 0 and 4. And then the curves in between, you could pick a few points, but I think they were kind of asymptotic. So they looked something like this. Was our vector field. So how do we solve something like this? This is actually going to be something like the logistic equation we saw for modeling. So we'll go over it now, and we can go over it again of how to solve something like this. Just got to remember your techniques of integration. We have all y's, so let's put all the y's on one side. dy divided by, and let's see. So you can kind of choose what you want to do with some of these constants. Sometimes it's nice to keep this 1/4 on the right. I don't know if it'll help or hurt us. Let's just multiply it over. So we've got y times 4 minus y. And then if we multiply the 4 over, sorry, that's a dx, equals dx. So we just always multiply and divide with these separable equations. You can't add and subtract. If you add and subtract these differentials by themselves, you can screw some things up. So divide everything. We'll just get 1 on this right side, multiply the dx over. And so we'll just have dx there on the right. Integral of dx, easy enough. Just going to give me an x plus a constant. And now we got to remember how to integrate this guy. So we've got a nice and factored expression on the bottom. And so this one's one where we have to use partial fractions. So we're going to have something like a over y plus b over 4 minus y is equal to the combined expression. So what do we get? We get a times 4 minus y plus b times y is equal to 4. And then we can pick nice values. So when y is 0, we will get 4a equals 4. A should be 1. When y is 4, we get 4b equals 4. And so we get b equals 1 as well. So nicely enough, easy constants for this guy. And so what do we want to do? We've got now sort of a separable, the sort of partial fractions decomposition in the differential equation. So we've got 1 over y plus 1 over 4 minus y dy equals dx is our differential equation. And now we can integrate both sides. So we should get natural log of y. You need to keep the absolute values for these guys. Because this occurs often, especially with things like 1 over y. Anytime you integrate and get a natural log, to undo that natural log, we got to exponentiate. And we need the plus or minus from the absolute value, because this constant isn't going to work like it has in kind of the past ones. In the past ones, so the c, our constant can be positive or negative. But so how do I solve for y in this guy? Well, we want to use our properties of logs, combine our logs. So we will have natural log of, and did I miss something? I did miss something. Anyone see what I missed? I'll give you guys a second. Common mistake. Chain rule, right? If I take a derivative of this guy, what do we get? We'll get 1 over 4 minus y times a negative 1. So this should actually be a negative. There. So mind the minus signs. So it's subtraction outside the logs means division inside the logs. And so we combine our expressions. We've got natural log, absolute value of y over 4 minus y is equal to x plus a constant. Again, the constant can be positive or negative, but when we exponentiate, what happens? So this is saying that y over 4 minus y is equal to e to the x plus c. And we need absolute values here on the left. So I think we saw this a day or so ago when we were first introduced these separable equations. When I have an e to the x plus c, it is common to write it as e to the c, e to the x. And this e to the c itself is just another constant. But we got to be careful, at least with these steps on the right, because this constant could be positive or negative. And so if we want to be extra careful, we can label our constants. This e to the c1, since c1 is positive or negative, the problem with exponentiating that is even e to a negative number is still a positive value. It's just a fraction, right? So where this second constant we get would be strictly positive if we would just stop there in our algebraic steps. And this is why we need our absolute value, because the absolute value now, when we want to get rid of it, well, it just tells us that y over 4 minus y can be plus or minus that. And again, I think we mentioned this, we can kind of keep playing these games with the constants just to simplify our notation, our need to keep writing things like a plus or minus. We could just call this a new constant, C3, where now C3, well, since C2 is only positive, if I make it positive, multiply by a plus minus, that means now it can be anything, positive or negative. So you can write C3, you could write it in minus infinity to infinity, or any sort of notation like that, just to keep track of what values this constant can be in. Okay, so that was manipulating all the constants. Where are we at now? We still are on the goal of solving for y. And so that's just kind of the remainder of the algebra that you got to remember how to solve these types of equations, a rational function when we're solving for y. So we want to multiply our y over. You've got to distribute, so we'll have 4 times c3 e to the x minus c3 e to the x y equals y. We then add and subtract to put all the y's on one side, y plus c3 e to the x y is equal to 4c3 e to the x. And this is one of those cases where you do want to be careful with what you are labeling the constants, and why I haven't combined this 4 times c3. You could, if you want to combine this 4 times c3, it's still going to be a constant, but that constant is going to be different from that one. So this is where it's absolutely necessary to actually use a subscript. Whereas these ones up here, it's kind of like we're just substituting c1 for a different constant. This one, you could keep the same c just as a note that now it's only positive. And then even here, we could then keep it just as c, because now we're back to being positive or negative. It's in this case where now I have 2 separate constants that could potentially be 2 different values if I want to combine that 4 in there. So let's just leave it out just to keep our c3, and then maybe at the end, if we want to do some notational simplification with reducing these constants with other constants that we want to call it, we can work that out at the end. Okay, so last step to solve for y, we factor. And so what do we get? We get 4 c3 e to the x over 1 plus c3 e to the x. And that's a good solution. One of the things that is common, I think sometimes we try to manipulate this other ways. So this is essentially the logistic equation, or at least one solution to a logistic differential equation. Other ways you will see it is sometimes we will manipulate the constants a little bit. We could write this as 4 c3 e to the x I could factor out the C3 in the bottom, but then it would be 1 over C3 plus e to the x. And now in this case, those divide. And so we're left with an equation that looks like 4e to the x over this 1 over C3 is just a different constant, which we can call C4 plus e to the x. Kind of a nicer way to write it, right? A little bit, just because now there's only one constant hanging out there. And since we haven't been given initial information yet, sometimes it's nice to write things in such a way so that it kind of reduces the number of constants we're kind of throwing in there. Especially if we are given initial information, well, now I only have to solve for that one constant. If I'm given initial information and have it in this form, might be a little more work trying to solve for C3. Other ways you commonly see this, sometimes they factor out, instead of having e to the x, we like to have e to the minus x in this expression for the logistic equation. So let's see what that looks like. We're really just going to factor out the e to the x from the numerator and denominator. And so it'll be C4 e to the minus x plus 1. And now these e to the x's can cancel. And so we get 4 over C4 e to the minus x plus 1. Any of those forms are good solutions. Any questions on any of that? So it seems like with these problems, especially with the harder ones, with the ones where the integrals of y give you these harder functions, absolute values and rational functions, it's almost like the hardest part is doing the algebra, since you guys should all be pretty masters, pretty much masters of all the techniques of integration at the moment. And then there's just a little bit to keep track of and kind of understand about what's going on with these constants. But other than that, it should kind of feel like getting back to some of the basics of calculus. Any questions? Okay, so let's do this activity. It'll give us some separable equations with mixing problems. And let me take a look at it. So if you go to the schedule, mixing problems, flow in, flow out. Let's see, it's 11:37. It's pretty basic, so I don't feel like I need to really get you guys started on it. I'd rather have you guys kind of take a look at it, think about it, and now practice modeling these differential equations and kind of understanding what a differential equation is saying. We talked a little bit about this when we introduced it, right? It's like anytime there's a statement about a rate of change, something is flowing in a tank, something is flowing out. There's a rate of change, especially if the units we use are something per time. So in these ones where we've got a salt brine is pouring into a tank and pouring out of a tank at 10 liters per minute. So anything per minute, per hour, per second is always a rate of change. So this should also kind of ring a bell of like related rates like you did in Calc 1. And this is very much what we're saying with these differential equations. So that's like a dy dt. And then we can model that with what it's saying. So it should give us a statement like dy dt is equal to 10 liters per minute. So I'll go ahead and let you guys get started on that. And then if you guys finish, I guess that's it for today. So if you guys get through it, let me know. Maybe we can talk about it for a second. And then if you're good, I'll let you guys go.